All right, we are going to be bringing this section 7.3 to a close here today, which is actually going to bring this chapter 7 on sampling distributions to a close as well. Okay, this is where we left off on the notes page yesterday, and I know that this example is all filled in for you, so I just want to talk through a little bit of this here to make sure that we are comfortable, because there is a distinction between probability problems that ask you just for drawing out a single observation versus trying to calculate the probability that an average of a sample is a certain value. So here we're talking about the Peanutty Peanut Company. Dry roasted shelled peanuts are placed in jars by a machine. The distribution of weights in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Notice what Part A is asking for. It wants us to find the probability that a randomly selected jar contains less than 16 ounces of peanuts. So I'm drawing your attention to the fact that this is just asking us to draw out a single observation from the population. Okay. So that means we need to be using information just about the population distribution, not the sampling distribution. Okay, so you can see here that I have noted that they told us in the problem that the shape of the population distribution is normal. The mean is 16.1, standard deviation 0.15. Okay, you'll notice that I also set up the probability question not with an X bar, because this was just a single observation, but we're looking for what's the probability that just a single jar of peanut butter, or peanuts rather, would have less than 16 ounces. You can see I did a normal CDF. I even, for added communication, drew a bell-shaped curve and labeled and shaded, and here we've got basically a 25.25% chance that a randomly selected jar contains less than 16 ounces of peanut. Okay, now if we were to look at part B, here they're asking us first to describe the sampling distribution of sample means if you were to take simple random samples of size 10 jars and find the average weight of the 10 jars. Okay, we're supposed to check our conditions for any of these that we need to check conditions for. Okay, so we're going to say what the center is of the sampling distribution, which should be right in line with the center for the population mean. We are going to say what the spread is. Okay, here's the formula on the formula sheet. Make sure you're dividing by the square root of your sample size, which would be 10 in this case. Okay, remember before we do that, we need to have checked that 10% condition, that 10 times 10, which is 100, would be less than or equal to all the jars from this company. And if we can say that that's okay, we're checking off that independence condition, which means it's okay for us to go ahead and calculate the spread here. Okay, and finally the shape. Because we were told in the problem that the shape of the population distribution is approximately normal, therefore, that's what these three dots here mean, therefore the sampling distribution is normal. And I can go ahead and kind of compile all this information together. Here's my information on the sampling distribution. This is the mean of the sampling distribution for X bar, and that is the spread, the standard deviation. Okay, so finally, we're coming down here and we're being asked to find the probability that if we were to take a sample of 10 randomly selected jars, now what would be the probability that of those 10 randomly selected jars, there would be less than 16 ounces of peanuts, here's the key, on average. So now we're asked to find a probability of an average. So we want to be using the details here regarding our sampling distribution, which is what we have right up there. And you'll notice that I'm now saying the probability that X bar is less than 16, not just X. Okay. So we have this information. We're going to put that in normal CDF. Honestly, the only piece that really changes here is the standard deviation is much, much smaller for a sampling distribution. And so we're using 0.0474 for that, and we come out with the fact that there is about a 1.74% chance that the average number of peanuts in 10 randomly selected jars would be less than 16 ounces of peanuts there. Okay. All right, so let's go ahead and move to the next page here. And this is actually an important concept that you could see pop up in some of the homework problems. If you see a problem mention a total, okay, a total here. Remember, these problems here regarding these sampling distributions are sampling distributions regarding means or averages. So if you're given a total, we need to convert the total into an average. Okay, we want to convert it into an average. And you'll see what I mean here with this example here. It says a study of rush hour traffic in San Francisco counts the number of people in each car entering a freeway at a suburban interchange. Suppose that this count has a mean of 1.5 people, okay, and a standard deviation of 0.75 people in the population, okay? So these are descriptors of the population distribution. I'm just going to jot that information down right here, mu and sigma, okay? This is for the population of all the cars that are entering at this interchange during these rush hour times. Okay, it says here that traffic engineers estimate that the capacity of the interchange, this is the total capacity, is it could hold 700 total cars per hour. Okay, now you notice they gave us a total here, and we need to try to convert this over into an average. They want us to find the probability that 700 randomly selected cars at this freeway entrance would carry more than 1,075 people. Okay, it's asking us to show our work, and there's a little hint there that says restate this event in terms of the mean number of people per car. So let's write down a little bit of information here. We know that our sample size says the probability that 700 randomly selected cars. So our sample size is 700. The population size represents all the cars at the interchange. Okay, so all the cars that would be passing through the interchange. We don't have an exact number for that. Okay, now we want to restate this as an average. And so we're given a total of 700 cars per hour are passing through. Okay, and we want to find what's the odds that if we were to pick 700 randomly selected cars at this freeway, that they're going to carry more than 1,075 people, okay, in total. Okay, in total. So if we took the 1,075 people and we split them amongst the 700 cars, now we're talking about an average of each car roughly holding 1.5357 people. Okay, this is what we're doing and what I mean by converting the total over to an average. We're taking the total amount of people, we're dividing by the total amount of cars, and so what we're really after is what's the probability that there would be more than 1.5357 people on average in each car. Okay, that's what we're looking for. Okay, so that's kind of the state step is when you state the given information, you state what the probability is that you're asked to find, and in this case we had to do a little bit of a conversion here first. Okay, in the plan step, since this is definitely going to require us to have the center and the shape and the spread for the sampling distribution, since this is a probability about a mean, we need to go ahead and describe those three elements here. So our center is going to be spot on with the center of the population distribution. Our spread, this is a formula that would be on the formula sheet. Okay, we know before we plug those in, we should do a quick 10% condition check here. 10 times sample size 700 cars, 7,000 cars less than or equal to all the cars at the interchange. Okay, sounds like this is probably a pretty large interchange. It would be nothing to have that many cars be passing through, you know. So that we're going to say that that makes sense. I'm going to go ahead and just check that off there. Okay. All right, so now we're going to make our substitutions here. The population standard deviation divided by the square root of our sample size gives us our standard deviation for our sampling distribution to be 0.0283. Okay, now we need the shape. We've got to be able to say that this is normal for us to be able to answer this probability question and use normal CDF. We cannot use normal CDF if we can't conclude that the shape is normal. Okay, now let's see here. It doesn't actually indicate, it doesn't indicate at all up here that the shape of the population distribution is normal, so I can't use that. But I do know that since my sample size is 700, and that's definitely a number greater than or equal to 30, according to the central limit theorem, I can conclude that the shape would have to be approximately normal. Okay, so I'm going to put this information together. Approximately normal. Here's the mean. Here's the standard deviation. So that's all in my planning step where I've kind of showed each of those pieces that I need and any conditions that I would need to show as well. Okay. All right, so let's go ahead and move to the do step then. The do step is when we actually get to perform the answer to our probability question. We're going to do our normal CDF. Okay, looks like our lower bound 1.5357, upper bound 10,000, mean 1.5. Keep in mind we're using these values here, 0.0238. This is going to come out to about 10.36%. Okay, so our conclusion would look something like this. There is a 10.36% chance that it's important you mention the sample size because this probability changes depending on what your sample size is because that's part of how you got your standard deviation to be the number that you got. So there's a 10.36% chance that in a sample of 700 cars, okay, so that's important that you're mentioning that. The average, that's another important word here, the average number of people per car exceeds 1.5357. Okay, so a few important phrases here. We're talking about having a 10.36% chance that in a sample of 700 cars, the average number of people per car would exceed the 1.5357 there. Okay. All right, just a few things that I want to touch on, make sure that we are comfortable with in this chapter. We had looked at two types of sampling distributions, one for proportions and one for means. You'll notice the measure of the center should be spot on as an unbiased estimator and right in line with what the population proportion or population mean is. These formulas that we have right here are actually on the formula sheet. You have to use that 10% condition though to get what the spread, the standard deviation is. And then please make sure that you're very careful. This is a notable distinction for the shape, whether you're talking about proportions or means. Okay, the central limit theorem is exclusive to only means. Okay, so for means, you have one of two ways that you could describe that the shape is normal, either if the population distribution was described as normal or if your sample size is greater than or equal to 30. If you're talking about proportions, you're back to that large counts condition where you're showing the number of successes and the number of failures has to be both greater than or equal to 10. Okay, and the final thought that I'm going to leave you with here is please make sure that you are not putting the cart before the horse, so to speak. When you are finding the details of the center and the spread and the shape for any sampling distribution, you should always begin by checking the necessary conditions. You actually have no business whatsoever stating the standard deviation or stating that the shape is normal if you have first not shown for normality for proportions the large counts condition, or if we're talking about means, one of these two pieces. And then for the spread, you need to show that 10% condition, the spread. Okay. Now, one final thing to remember. These conditions are not provided on your formula sheet, so they have to be memorized as they relate to proportions versus sample means, and there are a lot more conditions, unfortunately, coming your way, so it is very important that you kind of memorize these as we go. All right, that brings this chapter to a close.